Hello and welcome friends. In the last video, we discussed about wind as one of the meteorological parameters and some theoretical concepts useful for the air pollution studies. Now in this video, we wish to discuss about importance of local wind patterns in view of air pollution. We'll discuss about the formation of the pressure zones as well as convection cells, global wind circulation patterns, local wind patterns, velocity profile and use of Deacon's expression. So as you learn the content, you will be able to explain the formation of pressure zones and convection cells for global wind circulation, importance of local wind systems in air pollution studies, and also use of Deacon's expression for determination of wind velocity. So let's try to understand about the formation of pressure zones. Already you know about headless cell, ferrule cell, polar cell in each of the hemispheres. We also know that Earth is surrounded by envelope of the gases, and this envelope of the gases is bound with Earth's surface due to gravitational force. As we consider the placement of the Earth in relation with the Sun, it receives far more radiations within the equatorial region as compared to the polar regions averaged over the year. As more energy received at the equatorial region, the air in the vicinity becomes hot and it rises above. As it rises above, it moves towards the North Pole or it moves towards the South Pole. During its transit, it becomes cool, descend at the poles, and return back along the surface of the Earth towards the equator. However, as the Earth is spinning, rotating about its axis, a single cell of circulation cannot exist in each of the hemispheres, and hence actually there are 3 circulation cells in each hemisphere, making total 6 in north and southern hemisphere. The rising air leads to low the pressure near the surface, and sinking air leads to high pressure near the surface, as we discussed about the high pressure system and low pressure system in our previous presentation. Hence, it leads the formation of the semi-permanent pressure zones on the Earth's surface. Very similar to the formation of the pressure cells, we can discuss about the convection cells. In order to have the understanding better, let's assume that there is no any extraneous force in the form of tilt, rotation, as well as temperature. As we discussed about the heating in the equatorial region, the air warms and forms low pressure zone. This heated air sample rises towards the troposphere and it spreads toward the north as well as south pole. As it moves up and along, it cools. The cool air is dense and it sinks to the ground, creating high pressure zone at 30 degrees north. The air is sucked back towards the low pressure at the equator, and this describes the convection cell north and south of the equator. As we consider the polar region, at the poles, the cold air sinks, forming high pressure zone. It moves along and converges with the air moving along the surface at this cell 2. As both meets, it has to rise till top of the troposphere. Hence, it spreads towards the pole and equator, causing formation of another cells. In line with the formation of the pressure cells and convection cells, we can continue our discussion for the formation of the global wind patterns. So as you know, at the equator between these 30 degrees north and 30 degrees south, air moves from high pressure zone to low pressure zone to meet at intertropical convergence zone. Also, in between 30 degrees north and north pole, air moves from high pressure zone to low pressure zone at subpolar low. These are basic global wind patterns. Further, the earth rotates from west to east in reality. As one sees from the space towards the North Pole, the earth will be appearing to be rotating in anti-clockwise direction, whereas with respect to South Pole, this direction of rotation will be appearing as clockwise. In the northern hemisphere, Coriolis force causes deflection towards the right, whereas it causes the deflection towards the left in the southern hemisphere. Already we have discussed about this in detail. In the Hadley cell, air should move from north to the south. But as it is deflected towards the right due to the Coriolis force, in reality, the air blows from northeast to the southwest direction. This belt is the trade winds, as it is called, at the time of the sailing ships. These winds were supporting the sailing of the ships. In the next cell, that is feral cell in the northern hemisphere, the air should move from south to north. But actually, the wind moves from the southwest to northeast. This belt is of westerly winds or westerlies. Finally, in the polar cell, the wind travels from the northeast direction and are called as polar easterlies. The wind belts are named for the direction from which the wind travels. So, the westerly winds, for example, blow from west to east. These names hold for the winds in the wind belts of the southern hemisphere as well. As we consider these global wind patterns, that will assist us in order to understand the movement of the pollutant over the global scale. However, as we think of certain local wind patterns that will be assisting us in order to understand the movement of the pollutant over the local region. These local flows are important to understand because they determine the amount of the pollutant that will come in the contact with the receptor as well as the recipient. In fact, the local conditions may dominate when the larger scale flow becomes light and indefinite. Also, these local phenomena are quite significant in terms of transport as well as dispersion of air pollutants. Some of the local phenomena that we can understand are sea and land breeze, mountain and valley winds, urban and rural circulations, and flow around structures. As we move ahead, we will discuss each of these phenomena. The sketches drawn on the right side will assist to have the understanding in the better manner. So we already know that these land and sea breezes are wind and weather phenomena associated with the coastal belts. This breeze is a result of the differential heating of the land and water surface due to the incoming solar insolation. We also know that water warms very slowly as compared to the mass of the land. So land gets heated rapidly in response to the heating. So especially during the daytime or say in the clear summer days, the land mass gets heated rapidly, warming the air in the vicinity. This warmed air, as it reduces its density, it rises vertically, and this air is replaced by cooler air which is over the water body. As it reaches the substantial height, it travels towards the water body and it sinks over the masses of the air that are present over the water bodies. During the night time, the radiation causes cooling of the air masses in the immediate vicinity of the land. The warm air over the water surface tends to rise vertically over the water body. Hence, the cool air masses travel towards the water body, occupying the space created because of movement of the warm air vertically. As the warm air reaches the upper atmosphere, it gets cooled and further it travels towards the land mass and sink over the air masses present over the land, thus completing the circular flow. Frequently at night, the temperature between the land and water are smaller than during the daytime, and therefore land breeze has lower speed. Another phenomena is mountain and valley wind. The solar heating and radiational cooling influence the local flows in the terrain situations. So during the hot period of the day, as the surface of the slopes gets heated, the air adjacent to it is also gets heated. Having its density decreased, the air attempts to ascend along the upslope. Near the top of the slope, the air tends to rise vertically. However, along each portion of the slope further down the mountain, it is easier for each rising parcel to move upslope, replacing the parcel ahead of it rather than rising vertically. This upslope flow is called the valley wind. During the night, as the land masses gets cooled, the cool dense air near the surface descends along the surface. This current of the air is termed as downslope wind. To compensate this descending air farther from the slope is cooled very little, is warmer relative to the descending air, and hence it starts rising. Thus it forms sort of closed loop in the reverse manner, which was caused during the hot period of the day. When the downslope winds occur on opposite slopes of the valley, the cold air gets accumulated within that valley region. So here just if we consider the mirror image of this particular sketch on the right side, here this wind will be getting accumulated in the lower region of the valley. In the module 1, we have discussed about the various disasters, and you know that such an accumulation of the air and how the pollutants are getting trapped to lead a particular disaster. If such valley floor is forming certain slope towards a certain place, the accumulated cold air simply will roll down along that valley, and this is called as cannon wind. As we discussed about this mountain wind during the night time, and as we consider about this valley wind during the daytime, the another names for the mountain wind are Katabatic wind, and another name for valley wind is Anabatic wind. Urban-rural wind circulations cause the formation of heat islands. Urban areas have the roughness as well as thermal characteristics very different as compared to the rural surroundings. The urban regions are characterized by the presence of buildings which could be high-rise, whereas the rural surroundings are characterized by some low dwellings and presence of more greenery. In the urban region, this undulation and roughness affects the vertical wind profile as well as even the vertical temperature profile. As there is a presence of asphalt, concrete and steel-like material in urban areas, with the exposure to the solar heat, they heat quickly and have the high heat storing capability as compared to the open regions and green regions and low-lying buildings that are present in the rural areas. As a result, the urban areas are warmer as compared to the surrounding rural belts. Also, during the night, as compared to the surrounding regions, being the urban area warmer, they act as emitting body and cause the emission of the stored heat during the night. Also, if there is not strong air current, the air rises over the warmest part of that particular urban core, drawing the cooler air from the surrounding, from all the directions, forming certain typically shaped profiles. As the cooler air is drawn from the rural belts, this cooler air is replaced by the air which is present in the upper altitudes. Hence, there is a circulation path of warmer air masses and cooler air masses over the urban area, creating a peculiar effect termed as urban heat island. Also, if we consider this urban region as a whole, and if we consider the emissions that are taking place over that urban region as a whole, if the regional wind allows the outflow to take place in single direction and all that particular rising emissions gain the same direction as that of the regional flow, these emissions appear to be taking place from some stack-like source. Hence, such kind of the emissions coming over that urban region and traveling in the same direction as that of the regional wind are termed as urban plume. As we consider the wake-up flow, they also lead to some peculiar situations as far as accumulation and settling of pollutants are concerned. So, when these winds encounters obstacles in its path, say such as some structure, this flow is considerably disturbed and some turbulent wake is formed in the vicinity of that particular structure, causing eddy formation on the leeward side. If the structure is streamlined, this effect is not that pronounced. However, most of the structures are having the edges as well as the corners, and the formation of such a turbulent wake is very common phenomenon. This disturbed flow consists of a cavity with strong turbulence and mixing this wake, which is extending for quite a distance further in the downward direction. Though these particular studies can be actually experienced based on the observations, even the lab scale studies can be conducted through the wind tunnels in order to understand these wake-like effects. Usually, wind speed is measured at a height of 10 meters by making use of anemometers. So the variety of the anemometers already we have discussed about. However, as we think of the presence of the structures, the presence of the trees, the presence of some greenery, each of these lead to some typical situations in order to alter the wind velocity as well as its profile. So as you see in this sketch, even for the small height of 100 meters, certain tall buildings, tall forests, etc. may reduce the wind speed considerably. However, as we go on reaching in the high altitudes, this vertical mixing will be enhanced, and as we discussed about the boundary layer theory, accordingly after a certain height, the wind speed will be considerably high as compared to what it is in the presence of the tall buildings and similar structures. Also, as we consider the flat ground and ocean surfaces, here you can see that the wind speed is considerably more as compared to what it is over the rough regions. In order to have the wind speed measured at the standard height of the 10 meters by making use of anemometers like equipment, we can have that transform to its value, probable value at different heights. So as you see here, the Deacon's expression as expressed by u by u1 is equal to z by z1 raised to certain exponent p, where this u is speed at altitude z, this u1 is speed at altitude z1. So this z is known altitude. In order to determine the wind speed at some convenient altitude z1 by taking into account the surface roughness factors as 0.4 for built up, 0.28 for heavy forest, city and suburbs, and 0.16 for flat terrain, we can determine the height at the desired level. As we move ahead, this Deacon's expression in relation with the stability aspect we will touch once again. At that time, we'll have some more discussion as far as the wind velocity profile determination is concerned. So thanks for your attention, friends. As we move ahead, we'll discuss about the temperature and solar radiation as another meteorological parameters in view of air pollution. So bye till then. I wish you very happy learning. Thank you.